Welcome back. This is our truss problems, and we're looking at them in 2.17, and this is number 5. A little bit more complicated truss, but really not too bad overall. So let's make a couple of observations about our truss before we start out. First thing we can look at is the truss determinant, and if you do the formula, 2j equals m plus r, you're going to find out that it is determinate. So that's good news, and I won't waste your time going through that right now, but let's go ahead and look at some angles that we have in here. So as I look at this, and this is the first thing I want to do in every truss, is be sure I understand the geometry. You can see that my angle D is a right angle. That's what I'm going to assume. And then I've got a theta E here, and I've got theta B. And I can look and see that C is going to be right angle also, and I've got basically another, and I'm going to call this theta B1. That B2 rather. And similarly, same thing here. I've got theta A. So let's just start out and solve for theta A. And if I look at theta A, what I have is 2 feet, and I'm split by 2 feet vertically. And all that I've got to do is say that the tangent of theta A is equal to opposite over adjacent, and this holds true for all of them. And in this instance, that is 2 feet over 2 feet with, as I look at A, here I've got my adjacent, and then here's my opposite right there. So what I'm going to come up with is that's going to equal to 1, and then if I go to the tangent, inverse of 1 is equal to 45 degrees. So that's pretty easy. So what I can actually see is theta A is equal to 45 degrees. I can go around the sum of the interior angles of theta A, where my cursor is flashing, theta B1, and then 90. Those have to add up to be 180 degrees. So therefore, I can just go through and say that theta B1 has to equal to 45 degrees also. So that's pretty easy. Similarly, I'm going to come over and find theta B2, and I can see it's the same formula. So if I go tangent of theta B2 is going to equal to my opposite over my adjacent, and forgive me for going over this over and over, but I want to be sure you understand that. B2, my opposite is right here, and my adjacent is right there. And what I come up with is that ends up being 2 feet over 2 feet. That equals to 1. Yeah, so therefore I can say that theta B2 is also equal to 45. So what I get is a couple of relationships here. I can see that B2 is 45, and I can come over and I can similarly say that theta E is equal to 45 degrees. I think that's about all of the angles that I really need to find in this. I could go through and make some more observations and find my opposite inside here, which adds up to be the complementary angle of 90 degrees, and that will all be 45 degrees. So I've solved all my angles effectively, and I'll update my diagram. Okay, so we found our interior angles and we know what all of those are. So I'm going to real quick update my diagram here, and I know that this is 45 degrees right here, 45, and I also happen to know that this is 45. Similarly all the way around, and I won't draw them all, it'll just clutter up the diagram. So I've got that. And let's work on the very first thing and talk about our reactionary forces resulting from the pin and from the roller. So down here I've got a roller at point D, and I know that my roller only supports one reactionary force. So what I'm basically going to do is draw this as a reactionary force at D that's in the x direction. At E, I know that I've got a reactionary force as well, and I'm going to go ahead and put that in tension. A couple of reasons for that. One is because the geometry looks like it's going to pull off there, but the second reason we'll come to here in a little while. and I'll show you that. But I'm also going to go ahead and say, hey, this has got to be pulling up. Everybody else is pulling down. So I've got a reactionary force in E in the y direction. So I've got those forces all in, and those are all the external forces. So the very first solution that I want to do here is I want to go ahead and put in a little bit of thought and say, well, if this thing is not accelerating, some of my moments have to be 0, and I can choose any point that I want to choose to prove that. So what I'm going to do is I'm going to basically start out and I'm going to say up here that if the sum of the moments about any point has to equal to 0, I'll go ahead and choose an easy one, and I'm going to say the sum of the moments about E have to equal to 0. So when I look at that, what that means is I've got a moment at A, so that means the moment at A, and I'm going to put some signs on this. So that moment at A is going to be pushing down and left, which is going to go around counterclockwise. That's going to be a positive plus. The moment at C, again, a counterclockwise moment, plus the moment at E, well, that's nothing because it's at the same point, but I do have a moment at D out here, so you can see that D is going to be pushing such that it's going to want to rotate way and up, or essentially clockwise, so that's going to be a negative moment. So I just put these over the top here just to initially enter. So what I'm really going to do is I'm going to put a minus sign there. Those all have to add up to be equal to 0. So I come back and look at my diagram. What I can say is my force at A is 500 pounds, acting on a moment arm of 4 feet, plus another 500 pounds, which is the force at C, acting at a moment arm of 2 feet, plus a negative value, and the force at D is the reactionary force at D in the x component, acting at this distance, right there to there, and that distance happens to be 2 feet. That all has to equal to 0. So if I isolate this, what I end up with is I end up saying that R dx is going to equal to this sum, 500 pounds times 4 feet, or 2,000 pound-feet, plus 500 pounds times 2 feet, or 1,000 pounds-feet, divided by 2 feet. Makes my math pretty easy here. That ends up being 2. And what I end up with is this is going to equal to 1,500 pounds for R dx. So let me go ahead and write that in red here real quick. And I'm going to add that here at R dx, and I'm going to make this 1,500 pounds. Now I put my conventions in, so this is actually a negative if I talk about a scalar, but because I draw it with a vector, I just draw it with 1,500 pounds. So now we can come back and we can say 2 other things here. And what we're going to say now is we can also come back and we can say, you know what, I found R dx, and I can tell you that my sum of my forces in the x direction now have to equal to 0. So let's look at that and say sum of the forces externally acting on the truss equals to 0. Therefore, I can say that R, E, x plus any other x direction forces, oh, there's R dx, R dx have to equal to 0. So let's put these in with the proper notation. I can say R, E, x, which is positive the way I've drawn it, plus a negative 1,500 pounds, because it's going to the left, has to equal 0, or REX has to equal a positive 1,500 pounds. So that's pretty easy. So let's go ahead and write that in here, and we'll keep these forces in here. So that's 1,500 pounds. And the next step that I can come up and I can say the summation of all the forces externally acting on the body in the y direction also has to equal 0. So what do I have in y direction? I've got REY, 500 down, 500 down. So therefore I can say a minus 500 pounds, that's acting at A, plus a minus 500 pounds, that is acting at C, plus a positive REY, because it's up, have to equal to 0. That basically adds up to basically say that REY has to equal to 1,000 pounds, and that is up. And REX is right, the way I drew that. So let me update my diagram. And this is 1,000 pounds. Sorry about that. Let me fix that and make it 1,000 pounds. And what we've done is we've just solved for our external moments equal to 0, found RDX, solved for our summation of the forces in the x and the y direction, and now solve for REX and REY. So we've solved all of our external forces, and we'll move on to the nodes next. That's it.